The Casimir force is widely viewed as a force that originates from what is called vacuum energy. It is often invoked as decisive evidence that the zero-point energy of the quantum field is real, but there is an alternative way of examining the force, which could be considered far more fundamental. In 1948, Dutch theoretical physicist Hendrik Casimir was working at Philips Research Laboratories in Eindhoven. He was investigating the properties of viscous materials that contain micro-sized particles in a liquid matrix, which are referred to as colloids. Their properties are determined by the van der Waals forces. These are long-range attractive forces that exist between neutral atoms and molecules. As a side note, in 1873 J.D. van der Waals introduced the idea of intermolecular forces, but did not theoretically explain them. Then in 1930 Fritz London was the first to provide an explanation for the intermolecular forces in terms of non-relativistic quantum mechanics. Theo Overbeek also worked alongside Casimir and realized that the theory currently used to explain van der Waals forces did not properly explain the experimental measurements they had obtained on colloids. Casimir then worked with Dirk Polder and found a simple expression for the intermolecular forces with relativistic effects included. Their result is a generalization of the London van der Waals force and includes retardation due to the finite speed of light. Intrigued by the simplicity of the results, Casimir searched for a simpler explanation. After a conversation with Niels Bohr, who suggested that it might somehow be related to the vacuum energy, Casimir found that calculations based on vacuum energy further simplified when molecules are replaced by perfectly conducting plates. This is the calculation you will most often find in textbooks. The idea is that when two uncharged conductive plates are placed in a vacuum, a few nanometers apart, an attractive force arises. In a simplified classical sense, there is no external field present except for gravity, which should be extremely small in this case, so there should be no force measured. In a quantum vacuum, electromagnetic fluctuations appear and disappear as intermittent electromagnetic modes that span an infinite range of wavelengths in free space. In between the two plates, the larger wavelengths do not fit. The difference between the waves that can exist on the outside compared to those on the inside creates an effective net force that pushes them inward. The optical cavity formed by the gap between the two plates restricts the number of modes that can exist inside the cavity to those with wavelengths that are half-integral divisors of the separation. Due to the fact that this force falls off rapidly with distance, it can only be measurable when the distance between the objects is extremely small. On a sub-micron scale, this force becomes so strong that it becomes the dominant force between uncharged conductors. When the separation is about 100 times the typical size of an atom, about 10 nanometers, the Casimir effect produces the equivalent of about 1 atmosphere of pressure. Casimir was able to calculate the force by summing over all the cavity modes. The problem is that this quantity diverges, but it is possible to obtain a finite result by taking the differences in energy between the plates at different separations. Although this was Casimir's approach, it is often expressed in terms of zero-point energy of a quantized field in the intervening space between the objects. Treatment of the boundary condition in these calculations has led to some controversy. Casimir's original goal was to compute the van der Waals force between polarizable molecules. It is possible to calculate the force without any reference to the vacuum energy of quantum fields. In 1956, Yevgeny Lifshitz found a general theory for computing van der Waals forces between plates which are non-perfect conductors and was able to show that the Casimir force emerges as a special case. In 1975, Julian Schwinger found yet another way of computing the Casimir force without referring to vacuum energy. Then, in 1997, Steve Lamoureux quantitatively measured the force to within 5% of the value predicted by the theory. It is often quoted as the most famous mechanical effect of vacuum fluctuations. Generally, high-energy physicists view the Casimir force as a force that originates from the vacuum energy, but amongst the condensed matter community, the more popular view is that it has the same physical origin as the van der Waals force, which does not depend on the energy of the vacuum. The vacuum energy approach focuses on the macroscopic origin, whereas the van der Waals approach focuses on the microscopic origin. In specialized literature, the two approaches are usually considered as two complementary methods. But which of the two approaches is more fundamental? After all, the conceptual picture of the world in which the vacuum energy has a direct physical role is very different from the picture in which it does not. More recently, Robert Jaffe argued that the physically correct approach is one based on the van der Waals force, while the approach based on vacuum energy is merely a heuristic shortcut valid only as an approximation in the limit of the infinite fine structure constant. Building on this, Hrvoje Nikolić presented a simple general proof that the Casimir force cannot originate from the vacuum energy of the electromagnetic field. In his paper, he starts by examining the quantum vacuum approach and points out that one of the main advantages is that it is relatively simple to calculate. But he also points out that the electromagnetic forces are forces between charges. But where are those charges? The force originates from the boundary conditions, but the microscopic origin of the boundary condition is not taken into account. The vacuum energy explanation is not a full microscopic explanation. He then outlines how the van der Waals explanation works. The Casimir force is explained by the polarization of the medium. The polarization can be traced down to the microscopic polarizability of atoms. Classically, there is no spontaneous polarization, as the two molecules cannot simply decide which of the two types of polarization to adopt. From a quantum mechanical perspective, we could consider the two polarizations as a superposition. Van der Waals force could be considered a quantum effect. The vacuum energy explanation originates from boundary conditions. These originate from the fact that there is no electric field inside a perfect conductor due to a rearrangement of charges. Rearrangement of charges is polarization. The interaction energy originates from the correlation between the polarization and the electric field. This is van der Waals energy, which is fundamental because it does not depend on the phenomenological macroscopic parameter, the dielectric constant. At a macroscopic dielectric constant dependent level, it can be interpreted as either the energy of polarization fluctuations or the energy of electric field fluctuations. So although the vacuum energy approach is an effective macroscopic description, the van der Waals approach gives a fundamental microscopic description. As always, be brave, be curious, the truth is waiting for us. Until next time.